speak now, Francesco?
Sorry?
Yeah, we can hear you. Okay,
Okay,
good.
okay, great. So
All right,
thank you.
so our next speaker is Francesco Gavazzo, and he will present a work on a relational theory of effect and coeffect. And Francesco, please go ahead.
Thank you. So indeed, this is a paper about relational reasoning on effectful and coeffectful languages. So the first thing to do is to understand what we mean by effects and coeffects. And roughly, we can define effects as those program behavior that tells you what happens when you evaluate programs, besides, of course, producing values. Whereas coeffects are not about the what, but let's say about the how, and in particular about how code is manipulated. And to make that a bit more concrete, here in the bottom part of the slide, there is an example of a program which is both effectful and coeffectful. This is the one-time pad program that takes an input a message and produces a secret message. And it does so by randomly generating a key and using the key to cipher the text. So in that sense, the program is effectful because there is some probabilistic behavior which you observe when you evaluate the program. But that's not the end of the story, because if you look at the type of the program, then you also see its coeffectful components. The type of the program tells us not just that we take a message in input and returns a message, but that the message in input is a private one and the message in the output is a public one, which means that the type constrains the use, the way in which this program can use its code. So for instance, it cannot copy and store the input somewhere, because otherwise it would break privacy. Okay, so these sort of examples are not just in security. You can have them, for instance, in differential privacy, or even in settings where you care about the resources that you need for performing computations. And for that reason, there is a growing interest in languages, in programming languages, combining both effects and coeffects, and examples of those languages being linear Haskell and Granule, for instance. And there are some main features that all these languages share. In particular, they are mostly based on substructural, usually linear type systems, which means that you treat your data as resources. And together with that, you have graded modal types, which are just expressive types that tells you how code can be manipulated. So for instance, you can have types that tells you that your program is a private one, that you can copy a piece of data, or you can use it 10 times, and other things. And that is the, let's say, the coeffectful layer of the language. And it also comes with an effectful layers, which is usually given by algebraic operations like sampling from distributions, printing, output, rising exceptions, and so on and so forth, and with and monads to model the effects that are actually produced by these operations. Okay, so that's about the language, but here we are interested in reasoning about programs written in those languages, and also in reasoning about the properties of languages themselves. And in particular, the kind of questions that one may be interested in answering are, is that code elimination sound, or when does the evaluation order matter, or even are these types indeed ensuring my programs to be secure? And there are many ways to answer these questions, like denotational semantics or program logics. But the tool we are interested in this talk, the one that we study in our work, is an old one that goes back at least to an observation by McCarthy, beginning of the 60s, when he noticed that oftentimes you can better understand program behavior by studying how programs relate to one another rather than studying them in isolation. So, and indeed, if you think of the properties that I mentioned before, they can be modeled relationally. So for instance, you can model the property that if effects commute, then the evaluation order is irrelevant by stating that the two programs here in the slides are equivalent. So they are related by a suitable notion of equivalence. And prompted by that observation, people have developed relational theories of programs, which roughly means that you define relations between programs and study them as first-class citizens. And that has some advantages. In particular, it is a kind of concrete approach to semantics in the sense that it is based on operational semantics. So you don't need a denotational semantics or expressive logics, which may be difficult to find. But at the same time, because it is based on relational mathematics, logic of relations, and similar things, it has nice mathematical properties, such as compositionality, for instance. And you can see all of that because researchers have developed relational theories, first for pure and then for effectful programming languages, giving rise to notions like contextual equivalence, logical relations, bisimilarities, and many others. So the question is, what about coeffects and what about effects mixed with coeffects? Well, and it is kind of a surprise that if you look at the literature, there is almost nothing about general relational theory of coeffects. And that's kind of weird because if you look at deeply coeffectful properties of programs, they can be easily and naturally modeled relationally. So for instance, if we think back about our example with private code, then we may say that a program is secure if we pick an external observer that just observes the outcome of the program. And just by looking at that outcome, she cannot infer any information on the private input. And this idea has been modeled, giving rise to the notion of non-interference, whereby you say that a program is non-interferent if whenever you give it to input to private input, which may be different, and you pick an external observer which has just low permission, meaning that she's not allowed to inspect private code, then she cannot tell you anything, she cannot discriminate the program, but just by looking at the outcome. So this is a form of a relational property in a way that models the idea that a program is secure. And there are many others in the literature, like proof irrelevance or metric preservation, for instance. So why is that the case? I mean, how comes that you have these coeffectful properties which are relational in a way, and there is almost no general relational theory of languages with effects and coeffects? Oh, by the way, I forgot to mention the previous property non-interference becomes even more interesting if you look at it in a probabilistic setting, for instance, where you have the notion of probabilistic non-interference. So these sort of properties mix well with other effectful properties and give rise to even richer relational notions. So how come there is no general theory of relational reasoning for effects and coeffects? Well, one of the reasons is that when you move, let's say when you inject coeffects into the world of, let's say, pure or effectful languages, there is some kind of gap in relational reasoning. In fact, in traditional relational reasoning, programs are either equivalent or not. They are either related or not. So you deal with binary relations. Whereas if you move to a coeffectful setting, we have already seen that, although informally, that the observer capabilities plays a role. So you may have programs that are considered equivalent from an observer with low permission, but which can be discriminated by an observer with high permission. And that deeply impacts the relational theory behind this sort of reasoning. So for instance, if you take the notion of compositionality, as one is used to in the ordinary theory of program relations, then you see that coeffectful languages are not compositional. You take two programs which are equivalent for a low user with a user with low permission, and you put them inside a context, and that context may just interrogate the private code and then change the outcome of the program according to that code. And in that way, you lose compositionality. Okay, and that led us to the contribution of our work, which is essentially to have filled in this diagram that you see on the slides. And a bit more specifically, what we have done is to define a general relational theory for effectful and coeffectful languages. And our theory is based on a calculus of ternary program relations. And we use that calculus to define many notions of program relations and refinements, such as contextual equivalence, applicative by similarity, logical relations, and others. And we do so in a kind of uniform way, relying on algebraic principles, essentially. And in particular, we rely on the notion of a relator and on the new notion of a corelator, which are general relational constructions that we have introduced to model the action of effects and coeffects at a relational level. And using this structure, we have proved general compositionality theorem for all the notions of equivalence and refinement that you see in the diagram, where, of course, we need to understand what we mean by compositionality. Okay, so I would spend the remaining part of the talk just giving you an outline of some of the technical development behind our paper, beginning with the language that we have considered. So what we have studied is sequential high-order languages with linear and recursive types, enriched with graded modal types, which, as I said, are ways to capture at a static level how programs can manipulate code. So again, you can say that the code can be copied or erased, how many times it can be used, and so on and so forth. And that's the coeffectful component of the language, which is given in the static semantics of the language. The effectful part instead is given, let's say, the dynamic semantics, and in particular, we consider algebraic operations to produce effects. So you have operations like sampling from distributions and printing outputs and similar things. And we use monads to model the effect of those operations. And in particular, we give to our language a monadic operational semantics, whereby the operational semantics pick a program and it evaluates to a monadic value. So for instance, if you take the maybe monad, then you recover the usual evaluation semantics with divergence, of course, but you can also take the subdistribution monad, let's say, and in that way you obtain probabilistic operational semantics. All right, and on top of that, we have defined relational theories. Now, as I said, our theory is general and rather algebraic oriented, but obviously there is no time here to show you what I mean by that. That would require me to introduce some algebra, and there is no time to do that. Instead, I will show you a concrete notion of equivalence, namely applicative by similarity, and I will use that as a vehicle to show you the main theoretical constructions behind our work. So, quick recap of what is applicative similarity and bisimilarity, beginning with pure languages, so no effects, no coeffects. And what's the idea behind that? Well, you pick two programs and you say that they are bisimilar if they evaluate to bisimilar values, and two values are bisimilar if whenever you give them an input, you still obtain bisimilar programs. Now, of course, this definition is circular if you have things like recursive types, as we do, but you can overcome the problem by defining it coinductively, so as a greatest fixed point of a suitable functional. And these more or less the definitions, the traditional definitions of applicative bisimilarity. We can rephrase it to fit into our monadic framework, in our monadic operational semantic framework. First taking the maybe monad, and in that case, the first clauses defining an applicative bisimilation tell us that we pick two programs, we evaluate them. What we obtain now are two monadic values, so two values inside the maybe monad. And these two monadic values must be related by a suitable extensions of a relation over values to relations over the maybe monad. And these extensions can be easily defined and can be defined in general. You say that two monadic elements are related. If the first one is different from bottom, then so is the second one, and the two are related. And this way of rephrasing applicative similarity gives us a sort of blueprint to extend these notions to effectful languages. In that case, you keep the definition the same, you just replace the maybe monad with an arbitrary monad T, and you parameterize the definition with a notion of relation lifting, namely with a notion that tells you how you can take a relation and lift, extend the relation to the monad. And the notion of relational extension is a well-known one, and it can be defined in terms of a relator, and other terminology you can find in the literature is the one of Lax extensions. And I put here the definition, not because I want to go into that, but just to give you a taste of how definitions are. So this is a general relational construction. It is independent of the calculus types and other stuff. It's just a relational construction. It simply refers to monads and relation, and it has an algebraic flavor. All right, so far so good. And by the way, I forgot to mention the properties of our relators are precisely what ensures applicative by similarity to be well behaved. But that's just about effects. So how do we inject coeffects in all of that? So first of all, as you have already seen in the introductory part of the talk, now program relations depends on user capabilities. So the first thing to do is to move from binary relation to ternary relations, which here I call modal relations, but they are kind of creepy relations or substructural creepy relations, if you like, which are just ternary relations, which also take into account a possible state, which here is taken to be an element of a monoidal preorder. And you can just think about examples. So you can take security levels. In that case, the possible state tells you the security permission an observer has. Or if you are familiar with quantitative reasoning, you can take an extended non-negative real numbers. And in that case, it gives you the numerical distance between two elements. And the nice things about these modal relations is that their algebra is pretty much the same one you have for ordinary binary relations. So you can define compositions, identity, etc., and use them to define what is a modal equivalence relation. They form a complete lattice, so you can give definition both by induction and co-induction. And also because of that, you see that you can smoothly extend the definition of a relator to modal relations, because the algebra you need is pretty much the same one of binary relations. And using these facts, we can start to sketch what could be a notion of a effectful and coeffectful applicative by similarity. So we take the clauses that we have defined before for the effectful case and just parameterize them with respect to a possible state. And that is straightforward. Now, the main point is that now we are considering also modal values and modal types. So the question is when two values of a modal type should be related. And the intuition to answer this question is that modal types do not act on code, but they act on how code can be used, and in particular on the user capabilities. So if you think about the case of program security, and you take two values of a private type, then that private type is just telling you that if you have a low permission, you cannot inspect the code. And so you should regard those programs as equivalent. Whereas if you have a high permission, then you can inspect the code. And again, if you're familiar with quantitative reasoning, then the action of a modal type essentially tells you how to scale distances between programs. So how do we how do we describe the essence of this idea? We have done so introducing the notion of a corelator, which is, again, a relational construction close in a way to the one of a relator in the sense that it shares the same idea, but completely different in the actual definitions. In particular, if you are familiar with a bit of categorical jargon, relators are Lax extensions of monads, whereas correlators are graded Lax extensions of the identity comonad. And here the identity reflects the fact that you just act on program capability, on the observer capabilities and not on programs. And you see that because you're extending the relation just in a way that it manipulates possible states. Again, here's the definition. I don't want to go into details, just to remark that this is a general definition and it is rather algebraic one. Okay, so using the notion of a correlator, we can complete our definition of an effectful and coeffectful applicative by similarity by stating the two modal values are related if they are related by the correlator, essentially. And the main result that we can prove now about this notion of applicative by similarity is that if correlators laxly distributes over relators, then these structures are enough to ensure applicative by similarity to be compositional. And what does that mean to be compositional? Well, if you remember, if you take compositionality just as a translation of the binary case to the modal case, you lose compositionality. And that's because you're not taking into account the context. Here we can use correlators to come up with a finer notion of compositionality that now tells you that the equivalence between two programs in a possible state is preserved by context, provided that the programs are related not just by the relation, but the relations inside, let's say, the correlator. And this notion of compositionality indeed subsumes the one that you find in the literature, such as non-interference, metric preservation, proof irrelevance, and all their effectful extensions, such as probabilistic non-interference, for instance. All right, so let me conclude because time is running out. Summing up, what I showed you is a theory of effectful and coeffectful applicative by similarity. This is based on three main ingredients. The first one is modal relations and their algebras. The second one is the notion of a correlator, and the third one, the notion of a correlator, which is just the relational counterparts, let's say, of effects and coeffects. And crucially, we have proved, I've shown you that these structural properties are what you need to make your equivalence compositional. Now, as I said, in the paper, we do not deal just with applicative by similarity, but with a larger spectrum of equivalences and refinements, such as contextual equivalence, logical relations, and others like normal form by simulations. And remarkably, the same condition that ensure by similarity to be compositional ensures also all the other relations to be compositional. And finally, let me conclude with this last slide, which is just a visual impression. I don't want to explain that because I told you that the flavor of the paper of the relational theory is a kind of an algebraic one, whereas in this talk I was rather concrete. So if you look at the paper, these are the kind of formalism that you will find for performing relational reasoning. So which is a kind of algebraic and a 0.31 where possible. That's all for this talk. So if you have any questions, so please go.
All right, let's thank Francesco. Let's see if we have any question here in the room. All right, we have a question online. We can start with that. Have you considered making your monad graded as well as the comonads?
Yes, absolutely. This is something that one can easily do. We have done that in the paper just to somehow keep the notation and the framework as light as possible. But we can easily do that. Well, on the type system, you just put graded monads, and this is something that people have already been studied quite a lot. And on the side of the relational theory, you just have to replace the notion of a relator with the notion of a graded correlator. So because now it acts on the graded monads, and that is not difficult. And to prove the compositionality theorem, well, that's the part which is a bit more delicate. You have to replace this lax distributive law with a graded one, which is somehow mimic the sort of distributive laws that have been considered for giving comonadic denotational semantics to languages with graded effects and coeffects. But that's just a matter of a technical exercise, and it can be easily done, let's say.
All right. Any other question? If not, since we are short in time, I suggest we thank Francesco again.